this video, I'm going to go over the solutions to the curve sketching worksheet. In this worksheet, all you really had to do is try and follow the various different steps that we've already learned in order to try to sketch a curve of this function here, f of x equals e to the x over x. And I went ahead and told you already that the first derivative is this function here, and the second derivative is this function here, which should save you a little bit of time. But we still need to go through all those various steps that we've learned to figure out where is this function increasing and decreasing, what is its concavity, does it have any asymptotes or intercepts, etc. So let's start with the increasing and decreasing. Remember, when we're looking for increasing and decreasing along with critical points, we're always looking at the first derivative function, right? We use this first derivative function here. All right, so the critical points are going to be anywhere in the domain where f prime of x is undefined or equal to 0. So this function is undefined, f prime of x is undefined at 0. And so you could technically be changing from increasing to decreasing there, or vice versa, but it's not going to be a critical point because f of 0 is undefined, right? F of 0 would give you e to the 0 over 0, which is undefined. So it's not a critical point, but it is still a point that we're going to want to put on our real number line when we're breaking it up to test for increasing and decreasing. Okay, not a critical point though, because it's not in the domain. So we also want to figure out where is f prime of x equal to 0. That's going to be the other place where you could have a critical point. So that's going to be anywhere where the numerator of this function is equal to 0, right? A fraction is only equal to 0 when the numerator is equal to 0. E to the x times x minus 1. Now, e to the x is never equal to 0. E to the x is always positive. So the only solution here is going to be where x minus 1 is equal to 0. In other words, when x is equal to 1. So x equals 1 is our only critical point. But we're still going to break up our number line including 1 and including 0 because this place where x is equal to 0, you could have an asymptote or a hole, and you could still be switching from increasing and decreasing. So negative infinity to 0, Logie, ruining my video, bud, is our first interval. 0 to 1 is our second interval. 1 to infinity is the last interval. All right, so what we're going to do is we're going to take a point in each interval and we're going to plug it into the first derivative function and see whether it's positive or negative. Now keep in mind, e to the x, no matter what you plug in, it's always, always positive. So we can almost kind of ignore that when we're doing this test for positive or negative. So let's plug in negative 1. We're going to get e to the negative 1, e to the anything is positive, times negative 1 minus 1 is negative, divided by negative 1 squared, which is positive. Denominator is x squared, that's going to always be positive, so that's useful too. So overall, we're getting something that's negative in this first interval, which tells us that our original function f is going to be decreasing on that first interval. Now we plug in something between 0 and 1. Let's say plug in 1/2. We'll get e to the 1/2 is positive, 1/2 minus 1 is negative, and 1/2 squared, of course, anything is positive in the bottom. And so this is going to be negative as well. So we're still going to be decreasing on this second interval. And when we plug in something greater than 1, like 2, we'll get e squared is positive, 2 minus 1 is positive, and anything squared is positive. So in this last interval, we do get something positive, so f is going to be increasing on that last interval. All right, now f was undefined at 0, so this wasn't never going to be a max or a min anyway. But at x equals 1, we change from decreasing to increasing, so we're going to have a local, if we're going down and up, it's going to be a local min at f of 1. If I plug 1 into my original function, I get e to the 1 over 1, which is just e to the 1, or e. So 1 comma e is going to be our local min. And f is going to be increasing on 1 to infinity, and f is decreasing from negative infinity to 0, and then union from 0 to 1. And the reason we don't just squish this into one big interval, remember, is that f is not defined at 0. So that tells us our increasing and decreasing intervals. The next thing that we want to check is the concavity, right? We want to check for any inflection points and check the concavity of this function. Remember, For concavity, we're always using the second function, the second derivative function to test. Okay, so use the second derivative function, and our possible inflection points are going to be anywhere where f double prime of x is undefined or 0. Well, f double prime is going to be undefined at 0 again, when x is equal to 0. But just like before, that function is, or x equals 0 is not actually in the domain of your function, right? Because you get a 0 in the denominator here. So it can't really be an inflection point, but you could still be changing concavity there if you had an asymptote or a hole. So we have f double prime of x could change concavity at x equals 0. And then it could also change concavity whenever f double prime of x is equal to 0. So if I set the second derivative equal to 0, it's only going to be equal to 0 when the numerator is equal to 0. So when e to the x times x squared minus 2x plus 2 is equal to 0. All right, well, e to the x is never equal to 0. We said e to the x is always positive. So are there any solutions to x squared minus 2x plus 2 is equal to 0? And you could try to factor it, but it's not going to work. So in the end, you would have to use the quadratic formula to find any zeros. And remember that a quick test will tell you whether there's any solutions just by looking at b squared minus 4ac, right? That's the stuff that's underneath the square root sign in the quadratic formula, where this is your b, this is your a, it's 1, and c is 2. So b squared minus 4ac would be negative 2 squared minus 4 times 1 times 2. This is 4 minus 8, which is negative 4. That means there's no solutions, because if we were to plug this into the quadratic formula, you'd have a negative under the square root sign, so there's no roots here. This is never equal to 0. Right? No solutions, so there's not going to be any inflection points. But remember, you could still change concavity at 0 if you had like an asymptote, and so we still need to actually plug in, and we still need to break up our real number line with that x equals 0, where you could change concavity. So we've got intervals from negative infinity to 0, 0 to infinity. And we're going to plug a point into the second derivative function for each of these intervals. Let's see, if I plugged in negative 1 into the original second derivative function, well, e to the anything is positive. If I plugged in negative 1 here, I better actually do it so I don't make any mistakes. I'm going to get e to the negative 1 times negative 1 squared minus 2 times negative 1 plus 2, all divided by negative 1 cubed. Okay, so this is going to be positive in the end. It's 1 plus 2 plus 2, so it's positive on top. And negative 1 cubed is going to be negative in the bottom, so this is negative overall, which means my original function f is going to be concave down on that first interval. If I plugged in something bigger than 1, I'm going to get e to the 1 times 1 squared minus 2 times 1 plus 2, all over 1 cubed. This is going to be positive on top, positive times a positive, and positive on the bottom. So overall, this is positive, which means on the second interval from 0 to infinity, f is concave up. Right? Positive means concave up. All right. So now we can write out there's no inflection points because the only place where you change concavity is where the function's undefined, but we can still say that f is concave up on 0 to infinity, and f is concave down from negative infinity to 0. All right, so we're all set with the second derivative function here. Now we move on to other important parts of the graph. Let's start with x or y intercepts. So for x and y intercepts, we need to either set the function equal to 0 or set the x value equal to 0. Right, so for x intercepts, that's where we set the entire function equal to 0 and solve. Well, f of x is the function e to the x over x. that's only going to be equal to 0 when the numerator is equal to 0, but e to the x is never equal to 0, so it has no x-intercepts. For y-intercept, we do the opposite. We let x be equal to 0, so we actually evaluate this function at 0. We're going to get e to the 0 over 0. Uh-oh, we know this is undefined. So actually this graph has no y-intercept either. It doesn't cross the x-axis or the y-axis. Okay, cool. So that tells us some information. Now we move on to any holes or vertical asymptotes. And just as a reminder, the function we're talking about is e to the x over x. So holes or vertical asymptotes only happen when the function is undefined, right? So that only happens at x equals 0. F is undefined. And if we were to try to plug in x equals 0, we'd have f of 0 would be e to the 0 over 0. Now remember, anything to the 0th power is equal to 1, so we get 1 over 0, and anything non-zero over 0 means you have a vertical asymptote. Okay, we have a vertical asymptote at x equals 0. It's the only place this function is undefined, so we're not going to have to worry about any holes or any other asymptotes. Now, end behavior is where we determine whether the function has horizontal asymptotes or not, right? So we look at the limit of this function as x goes to positive or negative infinity. Now this might be doing something different if we're going to positive versus negative infinity. So I'm going to do these separately. Right? If they were both polynomials, it wouldn't really matter. So the limit as x goes to negative infinity of e to the x over x. As x goes to negative infinity, e to the x, maybe you recall, looks like this. Right? This is the e to the x function. E to the x heads towards 0, so the numerator is going to be heading towards 0, while the denominator heads towards negative infinity. So we have something really, really tiny and close to 0 on top, and really, really big on the bottom. So this limit is 0. So as x goes to negative infinity, right, for negative x values, we have a horizontal asymptote at 0. But for positive x values, it's going to be different because we have e to the x over x. As x goes to positive infinity, e to the x is going to shoot up towards positive infinity as well. And just x itself is going to go to infinity. So we end up with an indeterminate form of the type infinity over infinity. So by L'Hopital's rule, we can take the derivative of both and say that this is equal to the limit as x goes to infinity of the derivative of the top, that's going to be e to the x again, over the derivative of the bottom. Derivative of x is just 1. Well, the limit of this function as x goes to infinity, of course, is just infinity, right? The limit of e to the x is, as x goes to infinity is infinity. So the horizontal asymptote is only going to apply for the left-hand side of the graph, right, for negative x values. For the right-hand side of the graph, your function needs to be shooting up towards infinity. Now that we know all this, we can sketch our graph using what we did on the last page and using what we know now about these asymptotes. So let's start by sketching in any asymptotes we have. We know that we've got a vertical asymptote at 0, so I'm just going to draw this dotted line here at 0 as a reminder that this is an asymptote. And we have a horizontal asymptote at 0, but only for negative x values. So I'm going to draw this asymptote, but I'm just going to do it on the left-hand side of the graph. All right, any other important things to know? Well, we had found that there was a local min for this function when x was equal to 1 at the point 1 comma e. So e is like 2.7-ish, so I don't know. Let's say this is e here. We've got a local min, so something that looks like this. And now using what we know about this function, it's going to be decreasing from negative infinity to 0. So the only way to fit that into our asymptotes here, the only way to be decreasing this entire interval also to be concave down, is to look something like this. Right, that's the only way that you're going to be going decreasing downhill from left to right on that entire interval. All right, then what happens after 0? Well, your function's going to continue to decrease, right, so it's going to have to be coming down from positive infinity as you head towards 1, and then once you hit 1, you switch to increasing. So on our graph, I need to be decreasing, coming downhill after the asymptote, then I need to hit that point 1e, then I switch to increasing, and I continue to increase forever. All right, now does that fit with what we had for concavity? It looks like it does. For negative x values, the graph is concave down, and for positive x values, the graph is concave up. It's undefined at 0, so there's no inflection point, but this is exactly what it should look like.